All right, cool. Well, it is 10, and I do have a lot that I want to cover, so I am going to go ahead and start. Uh, do we need anything for this workshop? So I'm going to get into that. There was, I think, a download list, and it actually slightly changed, and I'll reshare that with everyone. But I'm actually going to encourage that you guys don't really. So there is code in this workshop, and there will be a finished project at the end of this workshop, so you will leave with something that you can use. But I don't really want you guys to focus too much on coding because it's a lot, and I'd rather you guys listen to what I have to say about the code rather than actually strictly coding it, and then just like going to the GitHub repo and pulling it. So don't worry too much about coding along. But if you want to, you can. Okay, so I'm going to go ahead and start since I don't want to run out of time. So, really excited for today's workshop. This is a simple intro to neural machine translation in 60 minutes or less. Hopefully less, but we'll see how far I can get. So I kind of already did the disclaimers, but I just wanted to give you guys a few disclaimers. One, if you get lost anywhere at any point, I don't really want you to worry. This workshop is going to cover a lot of, I think, dense material at a fairly high level. But even then, like, I would get lost. So if you do, don't worry about it. Just keep following along the workshop, and then any questions you have, just write them down, save them till the end, and I'll try my best to answer it. Two, I already mentioned it, you don't need to code along, but please feel free to. Like, if you have the stuff installed, but I don't think you'll actually be able to. I didn't share with you the data set, so you won't be able to train the model. But if you want to like write the Python script alongside me, you totally can, but you don't have to. I advise against it. And then the third disclaimer, much like you, I'm very low on sleep. I was up all night last night, so if I make any mistakes or if I sound loopy, I apologize in advance. Okay, awesome. So this workshop is all about neural machine translation, but what the hell is that? So neural machine translation is a family of language translation models. It's actually what most big tech companies and research institutions and all that stuff are using to sort of translate, well, computationally, of course, without the need of an actual live translator, to translate from one language to another. For example, if you were to go to Google's language translator, that's using AI. That's using a neural machine translation model to achieve that. So often, these models are encoder decoder models, and I'll go over what an encoder decoder model is. I don't think John and Hermes and Kevin went over that in their workshop. But yeah, so most neural machine translators are an encoder decoder type of model. I'll go into that in just a second. And basically the way that works is a source language is encoded and then decoded into the target language. So for today's translator, we're going to actually build a translator that's going to go from German to English. So that should be pretty cool. Oh, let me take a look. I don't know if there's anything in chat. Let's see. I think they touched upon it with a. Thanks, Lewis. All right, cool. I don't have two monitors, so I can't read the chat while I'm looking at while I'm presenting the PowerPoint. So I'll be switching back and forth. Okay, cool. So a brief overview of what an encoder-decoder model is. So like I was saying before, you have a source language, right? And you're going to have some data set of sentences in that source language. And what happens in encoder-decoder model is that those source sentences get encoded into something called a latent space or a hidden state space. They're kind of essentially the same thing. Then from the latent space, we have a decoder model that decodes it into the target language. Now, that's a little vague because there are a lot of different ways to do it. Our particular flavor of encoder decoder is going to be an LSTM based model. And again, I know I'm throwing out terms. I'll explain what an LSTM is in a second. But basically what we're doing is we're converting from one sequence to another with this sort of in-between. And this in-between is the latent space. And this is sort of something I always like talking about because for me it's the hardest thing to understand about AI, or it's the hardest thing for me to understand about deep learning. So I always like talking about it. The best way to think about this from a high-level understanding is imagine you're compressing a video, right? So imagine you've compressed a .wav or WAV file into an MP4, right? What you're doing there is you're trying to maintain the structure, and you're trying to maintain the underlying structure of what you're compressing, but you're trying to get rid of some of the fluff, right? And the fluff might be necessary for a higher quality, video or sound file or what have you. But you can still get the understanding of what was being compressed, and that's sort of what the latent space is. So the reason also why the latent space and some of this is so vague is because we can't read the latent space. So you and I as people, we can read the yeah, I see that the encoder is taking in this picture, he loved to eat, and it's taking those as tokens and then encoding those tokens. But when we go into the latent space itself, we can't read what's going on in there because it's some compressed mathematical representation of the sentence he loved to eat. And so the latent space, that learned representation of the sentence structure, of the grammar structure, of whatever elements compose a sentence, right? The decoder model takes that and is like, okay, this is what I'm getting from the learned representation. Now let me use what I know about the target language, and let me just apply it. I hope that makes sense. If it's still a little vague, or if it's still like not making complete sense, I can go over more in detail at the end of the workshop. I just don't want to run out of time. Okay. And so now, like I said earlier, we're doing an LSTM encoder-decoder model. So why are we using an LSTM? So first off, what does LSTM stand for? I don't know if John and co went over it, but LSTM stands for long short-term memory. And we use LSTMs for when we're dealing with sequential information, right? So meaning that, like, let's say you had weather data, right? And weather data changes over time. So there is a direct connection from where, let's say, a weather pattern or storm is right now compared to where it was before. They're not independent events. So, we use LSTMs specifically for sequential information in order to avoid something that's called the exploding weight problem. So I'm sure John and co went over in the previous workshop, went over how neural networks learn, and went over gradient descent, and went over all that stuff, and backwards propagation. So in the past, with something called recurrent neural networks, which were the basis for sequential neural network problems, there was a huge issue called the exploding vanishing weight problem. And basically what would happen is, because the sequence, there was so much information, or not enough information, well, that's not true. It's basically because there was so much information. When you would do backwards propagation, the weights for the hidden layer would either explode to really high values or vanish to near zero, or zero itself, but usually like very near zero. And basically the model wouldn't learn anything, right? It was not getting anything from those sequences, because in a recurrent neural network, you're kind of going through this feedback loop of the same information over and over again. But because you're dealing with a bunch of different tokens, if you're dealing with sentences or a bunch of different vectors all in the same order, you eventually just overload your neural network or your hidden layers, and you either get really high weight values or really low weight values. Lstm solved that problem. It employs a couple of different tricks, but the main trick it uses is something called a forget gate. And what a forget gate does is it basically says, okay, which members of the sequence do I care about in order to predict the next member of the sequence, right? So rather than taking in all the information every time you recurse through the tokens, through the sequence, I'm going to choose which values I care about most in order to impact my next decision, right? So to kind of give a practical example of that, let's say I have a sentence, right? And this is not necessarily always true. I'm just giving a very layman's example. But let's say you have a series of sentences, right? And you're doing it word by word, right? So if you go to look at the last bullet point, I have t-2, t-1, and t happened in this order. Then t+1 will be whatever, right? So we're trying to predict t+1. In order to predict t+1, we're using all the information we had before. t-2, t-1, t, whatever. Not all of those values are going to necessarily be important to predicting t+1. So what the forget gate does is it allows us to get rid of the stuff that's not important, so that way we're only working with members of the sequence we care about. And this improves computation time. This also prevents the exploding vanishing weight problem. I hope I gave a decent enough overview of LSTMs and why we use them. Again, any questions, I will expand further at the end. And so now, like with that, we're pretty much ready to get coding. It's really quick to talk about what our tech stack is. You could really use whatever you want. Like that's kind of the beauty. Like if you wanted to use PyTorch, for example, you totally could. But for this workshop, we're using TensorFlow, Keras, and with a little NLP flair, because we are dealing with natural language, we're using something called the Natural Language Toolkit, NLTK. It's a very impressive library. And of course, we're doing this in Python. So let me go back to my sharing screens. I'll answer a few questions in the chat real quick. Let's see. So Marco, I'm super sorry, I didn't read it in time. You asked something about similar to a compiler. What do you mean by that? I don't know what you're referring to at that point. Oh, the encoder decoder architecture. Is it like a compiler? In what you'd have to tell me in what sense. I'm not sure if it's a direct comparison. Marina, do I have to speak the language to do a translator? No, not at all. Not at all. Luckily, I do have a data set that I'll share with everyone at the end of the workshop. As long as you have the data for it, you don't need to know. I don't know German as much as I wish I did. So don't worry about that. Oh, and thank you, Armando. Armando, I love you. You're the fucking best. As long as you have the data set, you should be fine. Where can you normally find data sets? Kaggle. Kaggle is a great opportunity. There's a lot of really good natural language data sets out there. The one that I'm using is actually from Anki, I think is what it's called. It's like the flashcard. So a lot of people put flashcards from German to English. So that's what we're kind of using as our gold standard. That might not be like super accurate because it's open sourced since it's Anki, but you get a lot of data from it, which is really useful for us. Yes, don't worry, guys. I'll be sharing the code all at the end. You guys can literally take my GitHub repo and use whatever you want with it. Go make some, you know, robots and cool AI stuff. All right, cool. So I'm going to move on to the code. I will answer more questions at the end. Let's see here. So let me share screen. Application window. I apologize. Awesome. Okay. So for this workshop, I have the script already written for a couple of reasons. One, it's super easy for, and Armando can attest to this. Armando and I are colleagues. Armando's in the chat. Armando can also attest to this. We these TensorFlow models can sometimes be a little finicky with dependencies and all that stuff. So I have the script already written, and I'm not going to really go line by line with the code. I'd much rather go kind of block by block. I'm using Jupyter Notebook. It's really great for this kind of stuff. And just sort of explain what's happening. There will be some instances where I go line by line. But I really just want you guys to have a high-level understanding of what language translation models are and kind of how they work, since we only have an hour. And then for you guys to do some exploration on your own at the end. So hopefully that's cool with you guys. But feel free, of course, at the end and when you guys take a look at the GitHub repo, if there's anything you're just like, what on earth is this? I'll be online most of the day, so you can just send me a text and I'll help you out. All right, cool. So every good deep learning and machine learning and AI, project fundamentally has 3 steps to it, which makes it really easy to sort of remember. Thank you, Armando. Let me zoom in. Sorry about that, guys. How's that? Does that work for you guys? Awesome, awesome. Thank you, guys. Yeah, let me know if there's anything you need me to do. Please, I'll do it. I'm at your guys' disposal. All right. So there are 3 really easy. Well, they're not easy, but there are 3 simple steps to sort of having a successful deep learning model and or deep learning a script, and you can take this for any model you decide to make. The first one, of course, is getting data and cleaning it, and this is the least fun part. Luckily, the Anki data set that we're using is fairly clean already, so we don't have to do a whole lot. But in your when you're doing your own stuff, maybe not natural language processing or machine translation, you are going to need to clean your data set probably very thoroughly. Otherwise, you're going to get skewed results. So first step, we're going to load the data and we're going to clean it. Then we're going to actually build the model. And then once we build the model, we're going to evaluate it. And that's pretty much it. You load, build, evaluate. So let's go ahead and start with the first step, right? We're going to load the data and clean it. So let's see. So these, I'm just importing libraries. I'll run it too. So we're just importing some libraries. There's some use. I don't know how much Python everyone in this chat knows, but the important ones here are really just NumPy. NumPy is so useful for when you're dealing with arrays and you're dealing with data. So that's really the most important one. Pickle is just meant for storing like models. Thanks, Kevin. Pickle is really used for just storing models. And yeah, so first off, right, we're going to load the document. This function is literally just taking our, is going to take our data and load it into the scripts. And then what we're going to want to do, right, is this data set is a pair-based data set. So it's a pair of sentences. So we're going to have English sentences sorry, we're going to have German sentences as our source and English sentences as our target. So this data set is basically, you know, like on the left, you'll have Ich bin ein Mann, and then on the right, you'll have I am a man. And that's what we're going to feed into our network. If John and them talked about it, you know, the X value for the function we're approximating is German sentences, the Y value is English sentences. So that's what this is doing right here. This line, you know, it's Pythonic, but we're just literally splitting the lines into two. Then right here, we're going to clean the sentences. So what do we mean by cleaning the sentences? So in natural language, there's often a lot of like punctuation, spaces, you know, things that we don't need to compute on, right? We don't need, unless it's like a part of your system, like you don't necessarily need a comma in your sentence. You just need the physical words themselves. Like we're not concerned with a sort of grammatical representation. We're strictly concerned with word-to-word conversion. So that's what we do in this line of code right here, is we're taking out all the stuff we don't care about. And then we're, so, you know, and then we're also doing other normalization stuff. So like converting to lowercase, you know, removing punctuation, non-printable characters, you know, numbers we don't care about. And then we just, you know, after we're done cleaning it, we store it as a string. And now we have a cleaned pair. So for example, if my sentence was, hey, comma, I like the way you're dressed today. It, you know, you have spaces and commas in there, and you know, capitalization. Instead, it'll just be one like really long word. So that's what we're doing here. And then we want to save the data. So I can't stress this enough. When you save, when you clean data in more complicated data sets, it's often going to be a really arduous process, and it's going to take a lot of time. So save the data when you clean it, so that way you never have to do it again. So that's what this function is for. We're just saving the clean data. And I hope all that made sense. Again, I'm not looking at the chat right now. Actually, Armando, if you could do me a huge favor, if there are any really pressing questions that I need to answer, if you could just send me a Discord DM, I can see it pop up. I really appreciate that. All right, so cool. So we define the functions, and when you define the functions, I mean, it's just a matter of plugging and chugging. So our data set is DEU.text. This is the German to English text data set I was talking about. We're going to load it in as doc. We're going to make the correct English-German pairs. We're going to clean those pairs, and then we're going to save it. Always save your data set. And then just to sort of show you what it looks like, I printed it out here. Hold on, let me run this. Run. Yeah, so this is kind of what our data set looks like. So here we have English go, goes to ge. I didn't know that was German for go. Hi goes hallo, or hi is gru dot, run is lauf. So this is, we obviously, we have more than just 5 examples, but this is what our data set looks like. So now, once you save your clean data set, even though we have it already defined in the scripts, we're going to load it in, like just in case you, like, you know, close your script and you come back to it. You don't really need to run this code ever again, like this top part, because you can just load in what you already did. So this is just loading in the file. So this is our data set. And if you actually see, we have 221,533 pairs. So that's our total data set length, which is actually not bad for a natural language processing task. Obviously, more is better, especially when you're dealing with deep learning. But 220,000 is not bad at all. Now, for the purposes of this workshop, I don't want training to take you 500 years. So I limited the number of pairs to just 10,000. So I'm only taking the first 10,000 pairs. Feel free to, when you take the GitHub repo and play around with it yourself, feel free to use all of them. Feel free to use less than 10,000, more than 10,000. Just know that the more pairs that you use, the better your results will most likely be. I don't actually know what sort of like where it starts being marginal, where you stop really seeing gains in your performance. But I imagine if you used more of this data set, you'd see better results. Then we're going to shuffle the data set. So we're going to randomize it. We do this just so that way like if you actually look up here, we're going to shuffle the data set because in our data set we do have duplicate examples. So like for example, hi and hello and hi and grugat, run, lauf, and then run, lauf again. We're going to shuffle it because we don't want the model to get stuck on the same words for too long, right? So basically what I mean by that is, let's say in our data set we have a pair of translations for hi, right? And let's say we have 20 of those, right? If you were to have the model learn in order, right, of the data set, it would see hi translates to hello, hi, hello, hi, hello, hi, hello, over and over again. And remember that when we're doing deep learning, we're dealing with this forward propagation, backwards propagation in order to get optimal weights for our model. What's going to happen is those 20 samples are going to, because you saw them in order, it's going to skew the weights towards translating hi, hello really well, but it's actually going to detract from how well you translate everything else. So if John went over it, that's overfitting. You'll actually overfit on that one translation because of how many times in a row you see it. Now, obviously, 20 is not enough to cause overfitting, but when you're dealing with more real-world data, you can see thousands of examples all at the same, sequential order. So that's why we shuffle it. Then we're going to split it up into our training and testing data. So, yeah, we're going to split it up. We're going to do the first 9,000 pairs are going to be our training, and then our last 1,000 will be our testing. So 90% training, 10% testing. And then what I want to do is, once I've split it up into training and testing, I'm going to go ahead and save those that data. So I have my full data set, my training data set, my training set and my testing set. Armando just informed me that there's a really interesting question, so I will get to it right now. But that pretty much completes our loading data and cleaning data. Let me just see the question in the chat. Let's see, where is Ellen's question? Not pressing, just wondering, would this general method still be applicable for languages without spaces between words like Thai or Chinese? That is an amazing question. I love that question so much. Okay, Ellen, I will not forget that question because I actually talk about it at the end. But there's so much I want to say about that question. So, yes, but to sum it up, this model actually would do really poorly with like something like Mandarin or Japanese or and I'll explain why at the end. But this model, like particularly this one, will not do well. Now, would the general method still be applicable to languages without spaces between words like Thai or Chinese? But if you're talking about like cleaning data and preparing data, those languages kind of have their own quirks to them. I've never particularly worked with languages that are not Germanic or Latin, but those languages will have their own set of sort of necessary what's the word, necessary fixes to have models understand them. It's really an entirely different beast, especially when you talk about like more symbolic or like kanji-based languages. Like it's insane. But excellent question, Ellen, and I have more I want to say on it at the end. Thank you for the question. And I do see there are a few other questions in the chat, but I will address them at the end. So please don't let me forget. Please don't let me forget. Like I said, I'm very tired and I don't want to leave anyone out. Okay, awesome. So we cleaned the data. That was hopefully pretty easy to understand. I don't think I did anything too complicated there. If there was something, though, please let me know at the end or send me a DM on Discord and I'll absolutely help you out with it. So now we're going to want to build the model. Super cool. So this is where I think you guys are most interested in. Here we're going to be using Keras and TensorFlow. For those of you who don't know, I don't know if John covered it, so I'm pretty sure he did. But if he didn't, Keras is basically a wrapper for TensorFlow. TensorFlow in the past, it's gotten a lot better, but TensorFlow used to be very, very, very complicated to use. There was a lot of stuff that just made it really inaccessible. Keras made it way easier to use it, especially with the introduction of something called sequential models. So, man, the terminology is bad, but a sequential model is literally like Keras provides pre-built layers for your neural network. So instead of like having to write a whole recursive script and write, you know, the actual like functions from scratch for an LSTM or whatever, Keras literally just, you can say, oh, I want to have a model. Let me just add an LSTM layer. Let me add another one. I want it to be this size, and then you're done. Super easy, cookie cutter, but it gets the job done 99.9% of the time. So that's what we're using here. So the first thing we're going to want to do is create a tokenizer. So what is a tokenizer? So remember that we're dealing with language, and language we can't just put, you know, as much as I wish I could just type in a sentence and like have it be understood, we can't do computation on language directly. So we have to tokenize it and turn it into something that can be computed. So with the tokenizer, what we're doing is we're mapping words to numbers. That's quite literally it. There are some other ways you can tokenize, but the main way is you just turn it into a direct number. So you take all the words that you have in your data set and you just map them to numbers in order. It doesn't really matter how you map it, as long as every word has a unique number assigned to it. So now the next thing we're going to do is we want a function to define the max length. So the max sentence length. Why do we do this? So what we're going to do is, well, with sequence models that use LSTMs, LSTMs are not dynamic. So that's kind of one of the drawbacks to LSTMs I didn't mention earlier, was your input cannot change, meaning like the size of the input cannot change. So for example, you know, in English language, we have sentences that are 10 words long, 20 words long, or maybe only 2 words long. An LSTM is not able to sort of understand that difference. It's not able to work with that. So what we're going to do is we're going to find the longest sentence, right? And then we're going to pad all the other sentences to match that length with empty values. So for example, in this data set, I think the longest sentence is 9 words. If we have a sentence that's only 2 words, what we're going to do is we're going to fill it with 7 empty spaces. So that way it can be fed into the network. And you might be thinking to yourself, well, will the padding skew the results? Kind of. We kind of just assume it's negligible because it's empty. But if you have a really disparaged data set, meaning like let's say like the majority of your data set is like only 10 words long, but the longest sentence, you have one outlier that's 100 words. and if you try to match it to those 100 words, right? So you're now padding sentences that are 10 words long to be 100 words long. You will actually ruin your data. So it's really good in problems like this to get rid of outliers like that early on. We're just fortunate enough that we don't have anything super serious like that. I hope that makes sense. Okay, so now we're going to encode and pad the sequences, exactly what I was saying. We're going to tokenize and then pad. That's exactly what we're doing here. We're just making all the words into numbers and then padding the sequences with zeros, so that way everything is the same length. And now here's something we're going to do. We're going to hot encode the target. So we're going to encode, like tokenize and pad, both the input and the output. So our input is German and our output is English. So, we're going to, we're going to do that to both. But for the output, we're going to do something called hot encoding. And I don't want to harp on this too much, so I can talk about it more later because I don't want to run out of time. But hot encoding, basically, if you've never heard of it before, it's basically where you're turning, in this case, the sentences into binarized vectors, right? So you're basically turning everything into a category, and the way that we define the categories is based on a vector composed of zeros and ones. So for example, let's say I have, in a much simpler example, let's say I have 3 categories, red, blue, and yellow, right? We can't compute on red, so I want to determine whether or not something is red, blue, or yellow, right? So my output is going to be one of those categories. Now, how do we actually define those categories? Well, the way that we define it is through a hot encoding. So red, for example, might be 1, 0, 0. Blue might be 0, 1, 0, and yellow might be 0, 0, 1, right? And that's how we're able to like place or make predictions in a category. Now, the reason why it's a vector and why it's zeros and ones lies in linear algebra and a lot of stuff that I don't have time to cover. But just know that it's a binary vector, right? So what we're doing is we're turning our output into a series of binary vectors, right? And this is a must-have. If you're dealing with categorical data, you have to do that, no matter what. All right, awesome. So that being said, we're going to define the model, right? Defining the model is actually, look how short this is. I love Keras. I love Keras. Look at that. That's 1, 2, 3, 4, 5, 6. 6 lines of code, and you have yourself a really powerful tool that you can use. It's amazing. So let me just go over what this network, how this network is structured. So model, we're defining a sequential Keras model, and our first layer is an embedding model. Embedding layer. So what does an embedding layer do? What an embedding layer does is it's going to take our words or our tokens, and it's going to distribute the value of that token over a series of units, right? So why do we do this? So we embed our tokens further, one, for ease of computation, but 2, this is how we're going to sort of get a learned representation of our sentences, is by distributing these words across different units and then learning on those different units. So that's embedding. Then we have our LSTM layer, right? So remember how I said we're dealing with sequential data. We're dealing with a sentence. So, word 2 comes after word 1, and word 3 comes after word 2, and the order of those words mattered. So because of that, we're using the LSTM to capture that sequential data. Now we're doing something called a repeat vector. So what is a repeat vector? So what a repeat vector is doing is this is creating that sort of encoding layer. So once we have the LSTM capturing our capturing the representation of the sequences, we want to compress that and encode that. That's what the repeat vector is for. Oh, whoops, just deleted it. So whenever you're doing a sequential encoder decoder, you're always going to have a repeat vector in the center. Again, there's a lot more to repeat vectors, but that's what its use case is for. And so we encode, right, using an LSTM, right? So we encode using these two. But then we want to decode the sequences, right? So we're encoding the German into a latent space, and then from that latent space, we're decoding it with another set of LSTM, another LSTM layer. So that's what this layer is for. So this is the encoding, this is the decoding. Now Keras makes this really simple, but in better models and in more advanced models, you actually need to write them from scratch. Like you will write an encoder neural network and you will write a decoder neural network sort of from the ground up, so that way you have better granularity and more control over how your encoding and how your decoding works. But for the purposes of this data set, because it's super simple, and German and English share a lot of commonalities, it's okay. You're not going to get the best results, but you'll get sizable results for an hour-long workshop. And then this time distributed, what this is doing is, it's a little complicated, but it's because we're dealing with sequential data, but we're trying to map it to categorical outputs, like those categorical outputs being other words, so English words in this case. We have to distribute our learned sequence into those separate categories. That's what this is time distributed is doing. This is basically the last layer of the neural network, and this is the output layer. And if you're dealing with sequences, like a sequence-to-sequence model, you're going to use time distributed because you're distributing your output sequence to a bunch of different categories. I hope that makes sense, and if it doesn't, I'll be happy to help after the workshop. Okay, so now I'm going to load in my training data and testing data. So I'm just using the functions that I just talked about. We tokenize it, we get the vocab size, and we get the max length. This is what we're going to use for the embedding layer. So the source vocab size is 2,241, and the max length is 5. We're going to tokenize and get the size and length of the German language. So same exact process. And then we're going to get our training data ready. So we're going to encode the training data. We're going to tokenize it, all that good stuff. We're going to tokenize the output of the training data. And then we're going to one hot encode the output. Then we're going to do the same exact thing for the testing data. And then once you do all that, you're pretty much done. You define your model. You compile it. For this particular model, we're using an atom optimizer, and we're using categorical cross entropy. To understand why we're using these and how these work, you really need to dive into the math for it. The atom optimizer is just really good. There are some other ones you might be able to use here. I think you might be able to use, I think it's called L1, but atom works for categorical data pretty well. And to calculate loss, so to do gradient descent, to do, our backwards propagation, calculate the error, what we're using to calculate loss is categorical cross entropy. And this is pretty common when you're dealing with a multi-class output system. So we can get into the mathematics of this at a later date, but this is sort of bog standard. And yeah, so we define the model. We can plot the model here. This is just sort of showing this is like if you need to go and debug and you need to understand how your model is shaped. If you're kind of wondering what these are, remember that neural networks are all based in matrices and vectors. And so these are all just defining different vector sizes and dimensions. So then what we're going to do is then we're going to train the model. right? So I already did it for convenience sake, but you train the model, right? And then you fit it. So you're going to put in our training X data, our input, and then you're going to get our training Y data. Now, the number of epochs and the batch size that you use is really entirely up to you. I specifically chose this just for efficiency's sake. This maybe worked in like, I don't know what the total time was. I think it was like a minute. It took a minute to train. But if you're using more data, so instead of 10,000, let's say you're using 50,000 or 100,000, and instead of 30 epochs, you're doing 100 epochs, it's going to go for longer. Now, I don't know if John talked about what epochs are. He might not have. So just to let you know what epochs are, an epoch is basically one run of the data. So we're going to run the same training data through our model multiple times, right? And every epoch, we're running the full data set once. So this means that our neural network has seen this model this data set 30 times, right? And it's really important to find or to strike the right balance between the number of epochs and the size of your data, because too many epochs and too little data, you'll overfit. Too little epochs, too much data, you'll underfit. So you have to strike a sort of good balance between the two. And usually I would always suggest the higher amount of data you have, probably the more epochs you should have. But then again, it really depends on your data set, because there are some data sets where I would not recommend that. So it really just depends. But I hope that makes sense. So here we're just training the model. So once you've done that, you've built the model, you've trained it, now we get to evaluate it, right? This is where we get to say, are you hired or are you fired? Am I going to use you to translate my German grandmother's, birthday or birthday greetings, or am I going to go use Google? You should probably just go use Google, because this is not going to be anywhere near as good. So let's just go over really quick how we evaluate this model. So the first thing that we want to do is we want to physically see like the words themselves. Like we want to see it translated. So what we're going to do is we have this word for ID function. What this is going to do is it's going to take the output tokens that we saw. So remember, everything is tokenized. We're going to take the output tokens that we saw, and we're going to turn them back into real words. Now this predict sequence, this is the predict sequence is literally just us using the model. So we're going to make a prediction using model.predict. Model.predicted means just like plug in some data, give me the output, and plug in this data into the trained model. And that's what this is doing. We're basically making a prediction and then turning the tokens back into words. Pretty straightforward. Okay, cool. And then we're going to evaluate the model, right? So evaluating models changes. It totally depends on your problem space and what you're trying to achieve. So for our purposes, the way that we're evaluating the model is using something called BLEU, or BLEU. And the way that BLEU works, I don't want to get into it too much, but the way that it works is you're taking a look at something called n-grams, right? Man, you know what? I'm super sorry, guys. I should have made a slide for this. But basically, the way that it works is we're going to line up the real value. So the actual sentence, let's say the actual sentence was hello world, and the translation was, I don't know, whatever German is for hello world. Let's say we're translating from German to English. Let's say the correct English translation was hello world, and instead we got hello mom, right? What we're going to do is we're going to take a look at the different n-grams of that, of those two sentences, and then compare them. Do they match or do they not match? If they match, they get a 1. If they don't match, they get a 0. Right? And an n-gram is basically like sub-sequences. So a 1 gram in this case, for let's say for hello world, the first 1 gram would be hello, the second 1 gram would be world. But a 2 gram would be hello world altogether. So it's 2 tokens at a time. I hope that makes sense. It probably doesn't. At the end, if you guys really care about it, I can go more into it. But we're using this, like BLEU is specifically designed for language translation models. It was designed to help evaluate these types of models. So that's why we're using it. And we have 4 different scores here. So we're using 1 grams, 2 grams, 3 grams, and 4 grams. And the different length of the gram is basically saying how cohesive the translation is altogether, right? So the individual words, like you might have individual words that are correct, but groups or pairs of words might not be correct. And so like what we're going to see is that this model actually does really well with single words, but not with multiple words paired together. But I can go into that later. So again, we're just taking the data sets. This is just for posterity. Tokenizing it again, just so that way when we input it, we're inputting it correctly into the model. Okay, so first we want to look at our training data and see how well we did with our training data, right? And then we're going to take our testing data and really see how well our model did. So it's always good to take a look at both, because you want to see, okay, you really always want to look at the disparity between how well your model did in the training and how well your model did in the testing. Why? Because if your model did really well in training, meaning in school, your little baby neural network did fantastic, got straight A's, top of the class. But then as soon as it goes out into the real world, it fails miserably and isn't able to do your family proud, right? And we want to see, like, is it only good in school, or is it good in school and can it do well in the real world? That's the whole purpose of this. So we load the model, and then we are going to use the function here where we're going to evaluate it. So we're going to make a prediction and compare the prediction to the actual value. So the true value compared to the predicted. So we're going to evaluate the model on the training data. And so here we can see a few examples. So the source German language, German sentence was Tom flucht. I'm so sorry, I don't know German. Tom flucht, and the target was Tom swore. So we wanted to translate Tom flucht to Tom swore. And it actually predicted it. It said, okay, Tom swore. That was a good prediction. Here's ist abgeschlossen, and the target is it's locked. Our prediction was also it's locked. And we can keep looking at this. I mean, we can see like one that was sort of wrong, like wie kommt das is why is that, but what was predicted is how is that. So the training model is not perfect. But if we take a look at the BLEU scores, which is sort of our metric for success, the closer to 1 we are, the happier we are. That's the simplest way to put it. We see that on 1 grams, 2 grams, and 3 grams, right, our model did pretty well. Like, I'm satisfied with an 87, an 82, and a 71. Those are pretty good, especially for natural language processing tasks. Now, this is obviously not state-of-the-art, so I wouldn't be super happy with it, but it works. But then we notice that the model sort of drops drastically when you look at 4 grams. So that means groupings of 4 words together were not translated very well. But everything less than that, so groupings of 3, 2, and 1 words did actually fairly well. So now what we want to do is we want to see, okay, well, how does our model fare in the real world? So we're going to evaluate it then on our testing data. And here we're going to, let's look at Ich drückte sie. It says, I hugged her. But the predicted value was, I get you. So completely wrong, except for the word I. But then here we get something that's kind of more close, is the target was this is okay, and our predicted was that's okay. So it's really interesting because this is okay and that's okay is like they're obviously not one for one, but they're similar words, right? And that's probably because this is and that's are similar word vectors. And the learned representation of the model sort of like places these two tokens, this is and that's sort of in the same place. So it's not interchangeable to us, but it's almost interchangeable for the model. I hope that made sense. And if it didn't, I can expand after the workshop. But then we take a look at our BLEU scores, and we see that it didn't do so hot. It didn't do as well in the training. We see that it did a 50 on 1 grams, 40 on 2, 30 on 3, and 4 on 13. We see a pretty strict decline in success. And why might this be the case, right? Why isn't our model as good as Google's? Well, one, because I wasn't paid for this, so I don't have as much money as a Google engineer. But the real reasons why: we didn't have a whole lot of training data. We only used 10,000. The model is not super complex. Yes, it's only 6 lines of code, and that's awesome, and it's great for like a hackathon project, but it isn't like research state of the art. And so there's a lot that can be done to sort of fix this. But that being said, we've successfully created a neural machine translation model. I'm now going to run back really quick. Let me share that. So that's it for the code. I'm hoping the code wasn't like super hard to read, or that my explanations made sense. If they didn't, please lambaste me and tell me, so that way I don't do it in the future. But now, where do you guys go from here? So the things that you can do if you want to take this GitHub project and make it better: 1, improve the current model. The initial model is not well configured. Play around with the number of hidden layers. Play around with the amount of data that you use. Play around with the number of epochs, the batch size. There's so many hyperparameters that goes into a neural network that you can play around with and really make something powerful. It just takes some time. Unless you're using something like a genetic algorithm, which will do it for you. All right, next. Another thing you can do is learning different language translation. So this is kind of what I wanted to get at, Ellen, is that this model is really good for, and this is true for the state of the art as well, even though the state of the art is getting better at it. But these models are really good at translating languages that are already similar. So English, German, Spanish, French, these languages, they share a lot in common. Like, yes, German is different, of course, from all these languages, but in terms of like underlying structure, there's a lot that's shared. And because there's a lot that's shared, it's a lot easier to make one-to-one comparisons between words and to evaluate sentences. So something like Mandarin, or maybe something like Hindi or whatever, those languages are structured way different. Like Turkish, for example, is structured way different from English. Doing like a translation from Turkish to English with a model as simple as a simple encoding decoding will not work. But it will work for French and English, or French and Spanish. There's also just a lot of data for English language. So it makes it really easy to do English to something else, as opposed to, say, like Spanish to Mandarin. Okay, and then last thing that you can probably do is adding extra bells and whistles. So like attention. So this is a very simple model and not state-of-the-art. The state-of-the-art models actually use something called attention, and we call those attention models. I was actually talking to Armando about this. I wanted to do something with it, but it's just like too complicated for 1 hour. Even this is kind of too complicated for 1 hour. But there's a lot that you can add and read up on. And in the GitHub repo, I'll be putting resources for you guys to like go read and explore and do your own thing. And who knows, maybe, if this interests you, if this kind of work interests you, please explore, play around, add those bells and whistles, and make something really cool. So thanks for coming. I hopefully didn't go over time. Oh, Dude, I'm so I got it just at 11. I'm so happy. Okay, I didn't expect that. I thought for sure I was going to go over time. I hope you guys enjoyed it. This is a really big passion of mine. I love natural language processing. I love machine translation. It's super cool. I know I'm going to be kind of over time, and there are other workshops that you guys want to go to. But if you want to stay and ask me questions, I can stay for maybe like 15 minutes and try to answer them. And then if after those 15 minutes, any other questions you guys think of, just go ahead and send it to me on Discord. So yeah, awesome. But other than that, thank you guys so much for coming. I hope you guys enjoyed it. If actually, please tell me like if it was too hard to understand or if it was easy to understand. I want to know how I did, because this is a lot of stuff. So thank you guys. And Armando, thank you so much for answering some of these questions while I was presenting. Okay, so I'm going to go ahead and start from that question from Ellen. Ellen, I answered your question. The dataset will be in the repo. I don't know if the dataset will be in the repo. I might just have to send you guys a link to it. No, actually, I think I can put the zip file in the link in the repo. But if not, I will post it in the Discord. Dewan, can I build this with HTML? No, you can't. Well, I don't want to talk about it. Technically, you could. I mean, you can technically build any neural network in any Turing complete language, and I think HTML is Turing complete. So, yeah, Armand, you can build it with pen and paper if you have enough time. Yeah, guys, the source code will absolutely be available for you. You guys can do whatever you want with this. If you guys want to use this as the stepping stone to beat Google at their own game, go for it. Is this similar or kind of related to Markov model? Oh, yeah, Armando, yep. Yeah, Armando's input is very good here. Man, Armando's taking all my questions. I love you, buddy. You're so good at this. God, Armando is so smart, guys. All right. And transformers too. Yeah, so actually it's really interesting about transformers. So remember how I was talking about how like LSTMs suffer from so I was talking about how LSTMs suffer from like needing to pad sequences. Transformers, actually, you don't need to pad sequences. As far as I can tell, transformers don't really care about that kind of stuff. So state of the art actually uses transformers. I see less and less models using LSTMs and GRU units. Yeah, transformers are another great way to sort of improve upon what we built today. Can we have the link for the GitHub? I still need to upload the GitHub. I'm going to do that right now as soon as I close out this session. So, you know, don't worry about it. I'll be putting that in the look in the AI track channel. In the AI track channel, I will post it. I will make sure everyone gets added or whatever. Let's see. Good job. Thank you so much. Oh, thank you guys. Thank you guys so much for the really kind comments. I was actually kind of nervous about this because this is probably the most complicated. I feel like it's the most complicated workshop I've done in a while. So I appreciate that a lot. Connor, cool if I use Scratch. I mean, if you want to torture yourself, go for it, Connor. Listen, you know, I get it. I get it. We all want a challenge. Let's see. If you have time, what's your opinion on the black boxness of ML/NA? Oh man. Yeah. So this is a really good question. So machine learning and neural networks suffer from what's called being a black box. And basically what that means is, remember how I said the latent space, we have no way of reading it? We have no way of really knowing why neural networks work, and we have no way of really evaluating the innards of a neural network. So, you know, for example, we don't know why this was predicted. Like, we just know that it was predicted. and we use matrices and vectors to do it, but we have no idea why this was the prediction. And so this is actually like a big rift in the AI community, because you have people like, in fact, Armando and I, we have a research advisor, Dr. Finlayson, who's in one camp who believes that, neural networks are like not that great because we can't really evaluate them. And so, because we can't really understand what's going on in them, there are other methods that, the belief is that there are other methods that already exist or that can be created where we can evaluate what's going on the inside. But then there's the other camp that's sort of like, yes, we don't understand why neural networks work, but they're so powerful, like the results speak for themselves, like it's still worth using and researching. I personally, like, I kind of fall in an in-between. Like, I used to be in the right camp where, like, where it's like, I used to think, neural networks, the results speak for themselves. But after doing research in natural language processing and like in robotics and all this stuff, I'm like, yeah, I kind of wish I knew what was going on. It would make my life 10 times easier. So the black boxness kind of sucks, but it's par for the course. What's my LinkedIn? I think it's. I think if you look up Adrian M. Perez, it gets linked. I don't really know how LinkedIn is structured. It's like, I think it's something like that. If you want to add me, feel free. I'll add anyone who, from ShellHacks. I'll add you. We can connect. Link and build, all that good stuff. Okay, Connor, actual question. I know JS is 10 times better than Python. Oh, Connor. Oh, Connor. Should I use TensorFlow JS or take the plunge and learn Python better for TensorFlow Python? Okay, so this is a really good question, Connor, and I laugh because I hate JavaScript. Right. Right. JS is better than Python, sure. The thing is, like, Java, like, this is just getting into a topic of what languages are built for. JavaScript. Hey, Armando mods, ban Connor from the chat. No, I'm just kidding. Okay, so, but really, serious answer to your question. The thing is, like, Python is built specifically for this kind of work. It's the libraries and the community and the way that the language is built it's optimal for this kind of like research oriented AI related work. JavaScript, even though yes it has TensorFlow JS, it will run way slower than Python, and Python already kind of runs slow. Like if I would actually recommend, if you can do C++, like make your neural networks in C++ and have that stuff go dummy fast. But obviously I don't expect everyone to just jump onto C++ and start dealing with TensorFlow like at its base form, because that can get really annoying and tedious. And Python works just as well. But the thing is that Python is built for it. So if you really want to dive into AI, I would recommend, and like building models from scratch and doing all this sort of like, I would say very research intensive kind of projects, learn Python or Julia. Julia is really interesting. You might like Julia, actually. Julia's, I've never used it before, but it's more similar to JavaScript, I think, than it is to Python in terms of like syntax and operations. But Julia is like a JavaScript-esque language built specifically for AI. So if you're actually like interested, Julia is a really niche language that doesn't have a lot of attention to it, but it's really powerful. I love Julia. Like I've been dying to do projects in it. So I hope that helps you, Connor. And even though you have a bad opinion, I still respect the question. I'll take a few more questions and then I'll probably call it quits here. So Karthik, you asked, is there scope of improving neural networks? Any leads to that? What fields might deal more and more with such stuff? Improving, so yeah, I mean, neural networks, like like for example, I think a good example of that is like attention models. So attention models were developed, I think maybe like 3 years ago, 4 years ago, something like that, and they just sort of like in the past couple of years got really popular with encoder decoder models. There's always room for improvement. I mean, computationally, like we're coming up with new ways to sort of like make training faster and make the learning process more efficient. So another good example is transformers. So, well, like I was saying, you know, LSTMs used to be the go-to, the standard. But LSTMs have a lot of issues with them, and they're not the greatest. So transformers were made, and transformers can actually be trained in parallel. So transformers deal with sequential data, just like LSTMs, but transformers can actually be trained in parallel. So you can make the training process way faster if you have a GPU, as opposed to, you know, optimizing an LSTM network. So there's always room for improvement. In the field, I think your question is what fields in AI like are dealing with improving neural networks. There's a whole subfield dedicated to neural network architecture and optimization. Surprisingly enough, NVIDIA actually, like some of the like best companies for that are like NVIDIA and Google. Well, not surprisingly, they're like the top dogs in some of this research. NVIDIA, Google, OpenAI. I mean, these guys have work that's like dedicated to not applying models, but like how do we design a good model? Like how, you know, asking that question and like even like trying to answer the question, why do neural networks work? So there's a whole subfield related to that. But if you're asking about applications of AI, I think, you know, biology, chemistry, physics, I mean, you can literally apply deep learning in so many places. That's kind of what makes it so beautiful and so powerful. I hope that answered your question, Karthik. And if it didn't, I can always try again. Let's see. And I hope this video will be uploaded. I hope so too. I think it will be. And if it's not, just complain to Yasmin. Okay, if there are no more questions, I'm going to go ahead and end the session here. Thank you guys so much, so much for coming. This was super fun. If you guys have any questions that you didn't think of at this time, just at me on Discord, and I'll try my best to answer you. I'll be online for most of the day. All right, cool. And yes, Amar, all the code is going to be posted. Give me like an hour. All right, awesome, guys. Thank you so much. Much love. Have fun at the hackathon. You guys are going to do great, AI related or not. All right, cheers.